So our next speaker is Bohdan Mazhar, with title of his talk, The Deformational Properties of Smooth Functions on Klein Bottle.
Thank you. So welcome everyone. I'm glad to give a talk on the conference, and talk is based on the work on my PhD thesis I'm doing right now, and this is a joint work with my scientific advisor Sergey Maximenko, and the title and the topic of the talk is Deformational Properties of Smooth Functions on Klein Bottle. So let us begin with some introductory information. 1 second. Yeah. So we are concerned with classification of some topological groups related to compact surfaces. And to be precise, let M be a connected compact surface, and we are considering the right action of smooth diffeomorphisms on the space of smooth functions. This action is defined just by composition, as we can see here, and due to this action, naturally are stabilizers and orbits of the action arises, and we denote them like S, F, and OF. Study of and what is deformational properties? What do we mean here? It is actually homotopy types of these groups and of their subgroups, which are meaningful to inquire. And this study is this is a rather classical topic in the sense that study of homotopy types of spaces is classical type of problems which are being solved. And in particular, Sri Maximenko was working on it, and we'll talk about his work and how it is related to the work here later. For now, let us introduce class of functions we are concerned with, because actually we are looking not on all the smooth functions, but we are looking on the class F, which of functions that are this strictly saying just a subset of smooth functions defined on a manifold M, taken target in real line, and these functions are determined by two major properties. First one we can call local homogeneity, which means that having every critical point of given functions of this class, if we are looking at the germ of this function, it is smoothly equivalent to some non-zero homogeneous polynomial of two variables. And this polynomial doesn't have multiple factors. So yeah, here is how this polynomial can look like. And another property which defines functions in this class is something that we can call boundary components condition, or simply, what does it mean? That function takes constant values on every connected component of the boundary of surface, and these values are not critical. Okay, so looking on the functions of this class, we can also observe this class actually includes in itself all the Morse functions defined on the manifold, and Morse functions, it is well known that if you're considering the space of smooth functions as a topological space with strong Whitney topology, then Morse functions, just a subset of the space, is open and dense subset. And this class F contains all the Morse functions, which means that it is pretty hefty class, and it is reasonable to work with it. And yeah, another concept which was already mentioned today and which is important in this work is Rieber graph or Cronrod-Rieber graph, or any other names actually related to it, and we call it Rieber graph. And it is just a quotient of the manifold M with the connected components of the level sets of a given function. So yeah, as we see here on the picture, if we have some surface and we have something that represents real line, and we have our function f just a projection function, then we can divide all the level sets into this quotient, which we see here, and which is graph, and we can observe that actually all the edges of the graph correspond to connected components of level sets, and all the vertices correspond to the critical level sets. Okay. And another slide about notation, about what we are doing here. So given function from the class which we described, given some closed subset of a manifold, which is typically some collection of boundary components, maybe some critical points, but mostly it's a collection of boundary components of M. And given these two things, we can define the following things, following groups. So first of all, it is a group of diffeomorphisms that are just diffeomorphisms of a surface M that are fixed on X, which means that they are identity on X. And with the same thing with subscripts ID means that we are looking at the path connected component of this group, component that contains identity. And yeah, talking about path connectedness, we endow this group with strong Whitney topology. And all others we will be talking about too. So yeah, another notation is the stabilizer of F, which fixes subset X. It is the same with respect to action of this diffeomorphisms. And again, subscript means the path connected component of identity. Then there is a notation for the as well orbit of F that fixes X. And again, if we are having the subscript F, it means that we are concerning ourselves with path connected component of F in this space. And another notation is intersection of identity component of diffeomorphisms of surface M that are fixing X with respective stabilizers of F. We are denoting as S prime, and it is just a useful notation. Okay. This is important result I briefly mentioned before, and the result, like to be actually honest, it is like compilation of results and not in their all their generality, but in some particular case in which we are with which we are concerned here with. And these results are based on the work of the Francis Sergera, and they are formulated and proved by Sergei Maximenko. And what are we here interested in? We're interested in the fact that if we are looking at the function of the mentioned class F, and this function is defined on a manifold M, and it takes value in P, where P can be either a real line or unit sphere, one-dimensional. And yeah, we are talking now mostly about real line, but also for the S1 as well. And if X is a collection of boundary components of M and maybe some critical points of F, then we have the following. First of all, I'm not mentioning it here, but this group, which is not the group, I'm sorry, this orbit, which is subspace of smooth functions, it turns out to be a Fresher manifold, and moreover, this map P, which acts actually just as a composition of, let me write it here. Sorry, not F here, but H. So this map sends every diffeomorphism from the left to the composition F with H to the right. So, and it turns out to be locally trivial principal fibration with fiber S prime F, which we were discussing before. And why it is interesting? Because this fibration can and gives rise to the long exact sequence which is related to the fibration. And it turns out actually that there is interesting condition. If identity component of stabilizer of F is contractible, then tail of this long exact sequence, we can cut it off, and we are having this short exact sequence actually. And it turns out, moreover, that we can say about the cases when this stabilizer, this identity component of stabilizer is actually contractible. So when it is not simultaneously, when simultaneously these three conditions are not taken hold. And these conditions are quite technical, and which with what we are really concerned here, for this identity component of stabilizer do not be contractible to be homotopically equivalent to the circle, M needs to be orientable. And we are here concerned with, in the topic of talk, with Klein battle, which is not orientable. So we have actually this short exact sequence with which we can work. And yeah, maybe at this point I can tell a little bit more about context. That this study of homotopy types of orbits and stabilizers is of smooth functions at all, and in particular of smooth functions of this class, is taken for now a lot of time. Not really a lot of time, but maybe good 10-20 years, and maybe even more. And it is done by Zasary Maximenko and by his colleagues and some other mathematicians. For example, here there is a list of surfaces that was studied, and some of them were studied to the very end, which means that homotopy type of the respective functions of the respective orbits and stabilizers associated with functions on disk and cylinder, two torus, and actually Möbius strip was completely described. And with this result we were discussing on the previous slide, I'm not mentioning it here, but in the process of establishing it, it turns out to be that all higher homotopy groups actually they are we know them. So the only open questions here are about this two, about mapping class group of S prime and about fundamental group of orbit of function. And this open questions were addressed by respectively Kudryavtseva, Maximenko, and Soroka about disk and cylinder, And this was a long series of different studies. And Maxim and Feshchenko done the studies of the two torus, and I'm here citing two of their works that closely related to the work we are doing here. Case of a two-sphere was partially studied by Maximenko and Kravchenko, and Möbius strip was studied by Maximenko and Kuznetsov. And I'm citing the work that is actually quite recent and it is closely related to. So yeah, and after that all, let me formulate main results which we are concerned with. So, talking about functions on a Klein bottle. Functions of this class. We have, first of all, we have some topological decomposition, which indicates three strictly distinct cases. The first two of these cases are related to the graph, to the rib graph being acyclic, and last one to having a cycle. And it turns out these three cases they are mutually exclusive and they are they're extensive, so there is nothing beyond them. First one is rib graph is acyclic, and there is some component of some critical level set which breaks, which if you are removing it from the Klein bottle, it breaks it into some disjoint union of open disks. And in second case, if graph is acyclic, there is some connected component of, I'm sorry, here should be regular level set of function, and removing it, we are having a partition into two open Möbius bands. And in the third case, we have a cycle, and then when we are looking at the image of some, there exists some connected components of some regular set which corresponds to the point on the cycle. And when we are looking at an image of this component, which is actually just a closed curve on a Klein bottle, and we are removing all this image under the action of stabilizer of from the Klein bottle, turns out Klein bottle is there is partition of Klein bottle into open cylinders. And in terms of this topological decomposition, yeah, there is some pictures, schematic pictures, for example, here of case 1, here of a case 2. I have not much time, so I will not draw a picture of a case 3. So let's move on. And yeah, actual theorems about the structure of a fundamental group of orbits. First of all, in case 2, so when we have partitioned two Möbius strips, it turns out that fundamental group of an orbit of a function is it breaks into the product of respective mapping class groups of stabilizers of the same function restricted to the Möbius strips with a fixed boundary. And yeah, and due to result of Kuznetsov and Maximenko I mentioned before, we know actually what these two groups look like. And here is roughly what they look like, where this symbol denotes some type of a Friese product, on which we are not taking time to explain it here, but there exists some groups, some finite number of groups of a certain type, which we can arrange in such a way which describes this, which actually is isomorphic to this mapping class groups. And with this knowledge, we actually not only knowing P1 of an orbit, but actually from the short exact sequence that we were seeing before, knowing that this is integers, we can determine mapping class group of S prime of a function in Klein. and it is about class of case of Möbius strips. And the final thing I want to mention here is a case or a cyclic case. So when there is a cycle on a RIP graph of a function, then there is we can establish some type of Vries product, which is actually quite similar to type of Vries product that is used here, but is not identical. So yeah, it is just note. And this type of Vries product we are establishing here is dependent on M, which is actually number of these fundamental cylinders or number of curves in the orbit of stabilizer of this curve we mentioned before. And yeah, and on gamma, where gamma is automorphism of respective group we will mention. And this Vries product is just a following semi-direct product, which makes a cyclic permutation by one of an elements, which with the generator of Z makes a cyclic permutation by one of the elements of G to the power of M and acts with gamma on the last one. And it's actually, yeah, we have not really much time to talk about the geometric sense of it, but yeah, having this formula, we can formulate the following result. So when RIP graph has a cycle, and with respect to the function f from the given class, we have actually two possible cases. They are exclusive to, and in first one, it is stated that for every diffeomorphism from the stabilizer of f, equality that actually means that this diffeomorphism preserves this curve we were talking about. If it preserves, it implies that it preserves its orientation, then first of all, M, this number of this cylinders can be only odd, and there is an isomorphism following isomorphism, where a fundamental group of an orbit is isomorphic to the G Vries product of M, just classical Vries product this time with Z, where G is a fundamental group of an orbit of restriction of function on the fundamental cylinder with fixed boundaries of cylinder. And in the second case, when this condition is broken, so meaning that there exists at least some diffeomorphisms from stabilizer which preserves curve C but changes its orientation, then actually there exists such a homomorphism gamma which to the square equals identity, and the automorphism of this fundamental group orbit of restricted function. And then there is an isomorphism of fundamental group of orbit with this funny Vries product we defined before of this group with that. And the very final thing is when we have double covering of Klein bottle with the torus, it is actually, we can prove that there are following subgroups. So when we are considering ourselves with the composition of phi with pi, where pi is double covering, and we are considering the respective stabilizers and orbits, the respective stabilizers and orbits and their mapping class group of the stabilizer prime and fundamental group of an orbit is on a function on a Klein bottle is subgroups of respective mapping class group of stabilizer prime and fundamental group of an orbit. So yeah, and this actually can be expressed directly in the terms of previous theorem. And unfortunately, we have no time to talk about the geometrical sense of it. And this is the end. So thank you for your attention. Sorry for a little bit of delay. And if there is any questions, I can.
Thank you very much for your talk.